Now we're going to talk about differentiation in multiple dimensions. This is essentially Calculus 3, as it's taught at the University of Arkansas, done rigorously. And I think we're going to start with section 6.2, and we'll circle back and come back to section 6.1 if we have time. So section 6.2 is about differentiating functions from RP into R. So functions whose domain is multidimensional and whose range is one-dimensional. And long around section 6.x, we will get into 6.6, we will get into functions where the domain and range are both multidimensional. Let's start by defining our coordinate vectors. So we're going to start with a number p, a natural number, and then if j is between 1 and p, j is also a natural number, so we're going to let E1 be the vector that in RP that has a 1 in the first coordinate, then a 0, p minus 1 zeros. E2 is another unit vector. It's a vector that has its 1 in the second coordinate. E3 and then eventually we've got EP being the vector that starts out with p minus 1 zeros and has a 1 in the fourth coordinate. So we have in the pth coordinate. So EJ then is a bunch of zeros, a 1, and a bunch more zeros, where the 1 is in the jth place. So we've got j minus 1 zeros, and then we've got p minus j zeros. And I'll point out that I have written my vectors without any little arrows over them. You are welcome to put little arrows in your homework if you want, or leave them out as you prefer. I'm going to be leaving them out. It just makes the notation easier, and we'll just hope it's clear from context which things with letters on them are vectors and which things are not. This is a fairly common convention in mathematics. Now we're going to define partial derivatives. These are multidimensional derivatives, as you know and love and expect them to be. So we're going to start out with G is an open subset of RP. And let's let f be a function whose domain is G, whose domain is multidimensional, and whose range is the real numbers. Range is one-dimensional. And we're going to talk first about the partial derivatives of this thing, and then at some point we're going to get sick of partial derivatives and come up with an entirely new way of doing differentiation. And then if x is a point in G and j is some coordinate, then partial 1 f of x, we're going to write, that's sometimes written as partial f partial x sub j. Let's call this partial jf instead of partial 1f, just to be general. At the point x, we can write that as our limit definition. That's f of x plus t times e sub j minus f of x all over t. T is now a real number, so we can take the limits and the differentiations just like you expect. Let me draw what's going on in this definition. Here is our open set G in, say, R2. Here is our point X. And then here, let's say that EJ is this vector. Then X plus T times EJ, that's tracing out this line. So we draw a straight line through G. And so here's how we can, here's another way to think of this. We're going to let fj of t be f of x plus t times ej. This is now a function whose domain is this green line through x that we drew before. So whose domain is, you can write it as all the real numbers such that x plus tej is in G. Then I is a subset of the real numbers. And because G is open, and we know there's some small ball around the point X in G of radius. Let's say the radius here is delta. So you can see that this contains an interval minus delta to delta, and then partial j f of x is just, if you trace through the limit definitions, that turns into fj prime of 0. So this is picking out the derivative in some specified direction and using that as your partial derivative, as your definition of derivative. Let's have an example. Let's let G be all of R2. And we'll let f of x, that's f of x1, x2, let's say that is x1 cubed times x2 to the 5th. Then partial 1f of, let's say 3, 4. That's the limit as t goes to 0. F of 3 plus t, 4, adding a t times the unit vector just adds a t in the first coordinate, minus f of 3, 4. over t. Limit as t goes to 0. We divide by t, 3 plus t cubed, 4 to the 5th, minus 3 cubed, 4 to the 5th. I don't really want to expand this out too much. And you all know how to take that limit. You all know how to evaluate that at derivative. That's going to be 3, and then a 3 squared, and then a 4 to the 5th. Then more generally, the partial derivatives of f at x1, x2, you just treat your second variable, the one you're not differentiating with respect to, you just pretend it's a constant and differentiate like you know how to do the first variable. So we like partial derivatives because we know how to compute them. They're very easy to calculate based just on the differentiation rules we know and love from Calculus 1. I should point out that technically I shouldn't be writing f of 3, 4. I should be writing f of the point 3, 4. You take the whole point and you feed it into f. But that is annoying to write. So it's a fairly standard shorthand is that f of 3, 4 is f of the point 3, 4. And more generally, f of x1, x2 is f of the point x1, x2. One more quick definition, quick piece of notation. So let's suppose that partial sub jf of x exists, let's say for all x in the open set G. That means partial jf, that's a function whose domain is also G and whose range is also the real numbers. And then we let partial jkf of x, that's partial k of the function, partial jf, so that this notation means you take the jth derivative first and then you take the kth derivative at the point x. And of course, these all come with the caveat, if the derivative exists, if the limit exists, then the partial derivatives exist. But we're not, but I'm not going to keep writing that over and over. I'm sure most of you saw in Calculus 3 that mixed partial derivatives, it doesn't matter what order you take them in, whether you take the derivatives in the first coordinate first and the second coordinate second, or the second coordinate first and the first coordinate second. And we are going to prove that that's usually the case, but first I'm going to give you one example of a function where the mixed partial derivatives aren't always equal. So let's let f of x1, x2, this is going to be a function defined on all of R2. This is sort of the least annoying function where you can make this work. That's sort of not saying something much. So we want the first coordinate times the second coordinate times the difference of the squares of the two coordinates divided by the sum of the squares of the first two coordinates. And notice our denominator is only 0 if x1 and x2 are both 0. So we'll put x1, x2, the point is not equal to the point 0, 0. 2 points are equal if and only if all of their coordinates are 0. So the only problem is the point where x1 and x2 are both 0, which we can write as x1 equals 0 equals x2, or as x1, x2 equals 0, 0. And at that point, we're going to let f of x1, x2 be 0. I'm going to go ahead and suggest that you go out and find a nice 3D graphing calculator and plot this and try to see what's going on. Or you can find a regular 2D graphing calculator and plot this for several fixed values of x2 and see what's going on with f of x1. But let's go ahead and compute some derivatives of this thing. It is a painful but doable calculation that if you're not at the origin, then partial 1 f of, I'm going to use x as shorthand for x1, x2, comes out to as x1 to the 4th times x2, and then 4x1 squared x2 cubed minus x2 to the 5th, with a denominator exactly what you get from the quotient rule that you all know and love. And the second derivative looks very similar. Minus x2 to the 4th x1 minus 4x2 squared x1 cubed plus x1 to the 5th. Then quotient rule denominator again. So partial 1 f of 0 x2, when you plug in 0 for x1, an awful lot of stuff is going to cancel out. You'll get a negative x2, partial 2f of x1 comma 0. Again, an awful lot of stuff cancels out, and you get an x1. And it's an exercise that these are still correct at the origin. So partial 1, 2f of the point 0, 0, that's partial 2, partial 1f of 0, 0. That's you take partial 1f, which is of 0x2, which is negative x2, and you differentiate with respect to x2 is minus 1. But the other derivative, partial 2, 1f of 0, 0, differentiate in the other way, you get plus 1. So there are some complicated and weird functions where the mixed partial. We've seen that mixed partials don't always have to agree with each other, but you probably remember from Calculus 3 that generally they do. So let's put down a proposition that tells us that, in fact, we can expect mixed partials to exist. I think I'll go ahead and prove this proposition in 2 dimensions. And you can generalize to higher dimensions without too much work. So we let G be open. Let's let F be a function from G to the real numbers. And we're going to let X be in G. Let's suppose that partial 1f and partial 2f exist and are continuous everywhere in G. And we'll suppose that the two mixed partial derivatives they also exist everywhere in G. This is why we need the first derivatives to be continuous. You need to be continuous to be differentiable. And they also have to be continuous at our target point X. They have to exist everywhere. They have to be continuous at this one particular point. Then the two partial derivatives, mixed partial derivatives, are equal at the point X where they are continuous. And let's write out the proof. So let's start by drawing this picture. Here is our set G where F is defined. Here is our point X somewhere in the middle. And then because G is open, there is some ball of radius R centered at X in G. And then we're going to pick a positive number epsilon. And then we're going to use the continuity of the partial derivatives. And we're going to let delta be, because partial 1, 2f is continuous at X, there is a delta 1, 2 greater than 0 such that if Y is in G and is also in the ball centered at X of radius delta 1, 2, then partial 1, 2 f of X and partial 1, 2 f of Y are close to each other. And we'll say they're epsilon over 2 close. And since these functions are all mapping into the real numbers, I can just use absolute values. And similarly, there's a delta 2, 1 for the other partial derivatives. And then we're going to let delta be the smallest of these three radii. So we're going to let it be the minimum of the delta 1, 2 and the delta 2, 1. So inside the ball of radius delta, the partial derivatives are close to partial derivative of x. And we're also going to let it make delta be less than or equal to r. And that means when we go back up here, when I draw a ball of radius delta around x, I can be sure the entire ball is in G. And that's good because this is what I'm going to do. I'm going to put a little square around x inside this ball. I'm going to grab these 4 points. And they form a square that's inside G. So we're going to let's name the coordinates of x, x1, x2. Then we're going to I'm going to want a name of the coordinates. So we'll let A be x1 minus delta over 2. B is x1 and plus delta over 2. C is x2 minus delta over 2. D is x2 plus delta over 2. So that the 4 points AC, AD, BC, and BD are all in the ball centered at x of radius delta. And here is what that looks like. Zoom in on this picture a little bit. Here is the point AC. Up here is the point BD. Then we've got a nice square with those as the top right and bottom left corners. We've got our point X here in the middle, and the whole thing is inside the set G. Now, what are we going to do with this? We want to talk about the derivatives of this function. So what we're going to do is we're going to use the mean value theorem. We're not going to use the mean value theorem on x. We're going to use it on a couple of auxiliary functions. So let's let g of t, we'll define that as f of bt minus f of at. So then if we've got at here and bt here, then g of t is just the difference of f at these 2 points. And then notice G is continuous on the interval from C to D. It's continuous, F is continuous everywhere in G, so we can do this subtraction. G is differentiable on, well, all we need is the open interval. And then G prime of t, you'll notice, is the second partial derivative of f evaluated at the point bt minus the second partial derivative of f at the point at. So g prime of t is the partial derivatives of f in this direction, here and here. So by the mean value theorem, there is a point, I'm going to go ahead and call it T again, because we're running short, we're going to need an awful lot of letters here. T in the interval from C to D is such that, then we'll put G prime of T in the middle. Then we'll put G of D minus G of C over here, over D minus C. Now let's remember what G prime of C is. It's partial to f of bt minus partial to f of at. And let's write out what that is. That's 1 over d minus c. And then this is going to come out to 4 terms. Comes out to f of bd minus f of ad. That's the g of d part. And then we have to subtract off from that f of bc. Then we get to add to that f of ac. And now the reason why we use this auxiliary function g instead of applying the mean value theorem directly to f, now notice that we've got the same thing. We've got a t in the second variable. So we can just think about the first variable. We can think of f just along this connecting line between AT and BT. So again, by the mean value theorem, there is an S in the interval from C to D such that we'll write it as partial 1 to f of st. Sorry, S is not in CD. S is in the interval from A to B. That's 1 over B minus A. Then partial to f of bt minus partial to f of at. We're applying the mean value theorem to the function k of s is partial to f of st, whose derivative is partial 1 to f of st. And then we combine this with what we've written before, what we know about t. We know what the thing in the brackets is. It's f of bd plus f of ac minus f of ad minus f of bc. The order you put them in doesn't matter too much. So we have that there is a point somewhere in here, some point st. So there is a point st somewhere in our little square such that the mixed partial derivative, the 1-2 derivative of st, it's equal to this complicated sum of four things. But notice this is a very symmetric sum on the right-hand side. There's sort of nothing on the right-hand side telling us that, you have to do the second coordinate first and then the first coordinate. So we're going to do a very similar argument. So for some sigma, we have that partial 1f of sigma d minus partial 1f of sigma c. That's h prime of sigma 1 over b minus a, h of b minus h of a, and then, oh look, we get exactly the same complicated thing we saw before, f of bd minus f of bc minus f of ad plus f of ac. The terms may not come in the same order, but they are the same. And then we use the mean value theorem for a fourth time for some tau between c and d. We have partial 1/2f of tau sigma. That's 1 over d minus c, partial 1f of sigma d minus partial 1f of sigma c, which we have seen comes out to exactly the same thing we saw before. Let's collect the positive terms and subtract off the negative terms. And since we've seen this before, we've got that partial 2/1f of st. So we've got these 2 points in our square here, our st and our sigma tau, such that the 2/1 derivative at st and the 1/2 derivative at sigma tau are necessarily equal. So the upshot of the last page is that there are points st and sigma tau with they're both, and you can check S and sigma are between A and B, T and tau are between C and D, so the furthest they could be from X would be over here. The biggest distance here would be delta over 2, delta over 2, delta over root 2. So these points are in the ball centered at X of radius delta. Guess it's delta over root 2. So we can say they're in the ball centered at X of radius delta, such that partial 2, 1 f of st is equal to partial 1, 2 f of sigma tau. And then we just apply our definition of delta. So partial 1, 2 f of x minus partial 2, 1 f of x. That's less than or equal to, by the triangle inequality, partial 1, 2 f of x minus partial 1, 2 f of sigma tau. Then we add to that partial 1, 2 f of sigma tau minus partial 2, 1 f of x. And now let's write that again. And we're using the fact that these two quantities are in fact equal to each other, so that I can write this as two partial 2, 1 derivatives. And then we just use the continuity of our partial derivatives. We said that each of these pieces is less than epsilon over 2 equals epsilon. So the conclusion is that this is less than epsilon for all epsilon greater than 0. And the only way that can happen, the only way you can have 2 points, their distance is less than any positive number, is if their distance is in fact 0. So we've got our conclusion, partial 1, 2 f of x equals partial 2, 1 f of x.